Hello again. So, we discussed in the previous part of today's lecture the application of Gattu variation in order to establish necessary conditions for a functional involving the function y and its derivative y prime or dy by dx. Okay. Now, we will take a particular example to use those Euler Lagrange equation that we derived and the boundary conditions to understand that better. Okay. So, for that let us take a geometry problem for which we know the solution already. Okay. The solution that you know already, when I state the problem you will know. So, let us take a coordinate system, let us say x and y, and I choose 2 points, a point here, a point there. Okay. So, let us say this point is x1, this is y1, that means the point coordinates x1 y1, and this is x2 and corresponding y. If I extend this further somewhere here, I will have y2. So, I have a point x1 y1, x2 y2. The question that I ask is that which curve I can that goes through this point 1, let us call this point 1 and point 2. Between point 1 and point 2, we can draw many curves that pass through this, right. So, we can draw a number of curves. I can draw this, I can draw that, I can draw this and a number. I mean, this is really a lot of different curves we can draw, right. Among all of them, there will be one that minimizes the length of the curve. Okay. You know the answer. If I give you 2 points in a plane and somebody asks you which curve will have the least length, immediately your answer would be that it is a straight line, because we can see that here, right. If I draw a straight line between point 1 and 2, that will have the least length. So, least length. So, this will be the curve of least length. We have taken a very simple problem for which we know the solution, right. Now, we will solve this problem using calculus of variations to convince you that among all the curves that you take, the straight line is the one that is going to have the shortest length or the least length between 2 points, given points x1 y1, x2 y2. How do we pose the problem? We say minimize the length of the curve L, what was j, which is functional, now L becomes the symbol for the functional with respect to y of x, right. Each of these, right, will be y of x. We do not know, actually we know the solution that this blue one is actually y star of x, meaning that this one satisfies the differential equation or the Euler Lagrange equation, right. We have to establish that now mathematically using calculus of variation. So, I have this minimum with respect to y of x, I have to find that y of x or y star of x, which is a straight line, L, the distance. Once I know a general y of x, if I want to get the length. So, normally for anything, if I have a curve like this, I take a small bit, okay, I take this small bit and use Pythagoras theorem to find that length of that, right. So, why Pythagoras theorem? Because this part here is dx and this is a right angle, okay, and this is dy for that curve. Everywhere curve has x, for every x there is a y. So, if I take this one, I get this Pythagoras theorem. So, this distance is going to be square root of dx square dy square, okay, and that is what we need to take and add up. We want a total length from here to here or our curve from here to here, we have to do integration. So, we have to do integration from x1 to x2 for our curve of interest, x1 to x2 square root of dx square dy square, we have to add it up. Okay. Integration needs the dx, we take the dx out, right. When I take it out, what I get is x1 to x2 integral 1 plus dy square by dx square or dy by dx, dy by dx, dy by dx square. I have taken out dx. We got a proper looking integral. Okay. Now, this thing here becomes our integrand f. In this case, that integrand f depends only on y prime, because in our notation y prime is dy by dx. Okay. So, what is our f now? F is 1 plus y prime square under square root. So, that is our f now, and let us recall our Euler Lagrange equations, which was dou f by dou y minus d by dx of dou f by dou y prime equal to 0, and then we had of course the boundary condition, right, the Dirichlet or Neumann are essential and natural. Now, we understand what is essential, what is natural in the context of this example. Dou f by dou y prime into h x1 x2 equal to 0, right. Now, let us substitute over here. So, this one dou f by dou y, there is no y in our f now, this is f, right, there is no y there. So, this is 0, and then we have minus d by dx of dou f by dou y prime. Y prime we have to take derivative of this f with respect to y prime, then we get 1 over 2 square root of 1 plus y prime square, and then we have to use the chain rule. So, this with respect to y prime square is there. So, if you take derivative, it will become 2 y prime. Okay. We take derivative with respect to only y prime, not as x, but that is here d by dx of the whole thing, this is equal to 0. Okay. Now, let us go there. So, we can see this. So, what we got from here is d by dx with the minus sign that we can take off, it is equal to 0 anyway, d by dx into 2 here gets cancelled. So, what we get is y prime by 1 plus y prime square under square root equal to 0. What does that mean? It means that y prime by 1 plus y prime square under root is constant, because derivative of a constant equal to 0, that is what we have. In other words, we integrated from this step to this step, right, we get this. Now, if you think about this, if you say this constant is some c, then I can write, I can take this other side, y prime equal to c times square root of 1 plus y prime square. I can square both sides, I will have y prime square equal to c square into 1 plus y prime square. That implies that if we bring that y prime that we have there, it will become 1 minus c square c square, or I get y prime is equal to c square by 1 minus c square under square root, plus or minus does not matter, it is just there either sign, but what we get is y prime is constant, because c is constant, right, that is what we had. Now, it says that y prime is constant. Y prime is constant means what? Our curve y of x is a straight line. So, that says that y of x is a straight line. That is what we wanted to prove, mathematically we got it now, right. So, Euler Lagrange equation, which is what we wrote here, this Euler Lagrange equation gave us what looked like a formidable differential equation, but actually turned out to be very simple, that y of x is a straight line. Okay. Now, let us also look at the boundary condition, that is this part, right. Let us consider again, note that the f that we have here is 1 plus y prime square under square root sign. Now, what this boundary condition is saying is dou f by dou y prime times h, right. So, if we do that, what we get? We had just done it here, right. So, this dou f by dou y prime is actually this, okay. This is dou f by dou y prime. So, that basically is. So, let us look at this boundary condition which is over there, where we have f which is this, and what it says is that dou f by dou y prime, which we had calculated already there. So, I will write y prime by 1 plus y prime square under root times this h should be equal to 0, that product at both ends, that is x 1 and x 2. Now, if we recall the problem that we stated, these points x 1, y 1, x 2, y 2 are given, meaning that y was specified at both these points, y 1 was specified, y 2 is specified. At those points we cannot take variation, because we are not allowed to perturb there, it has to be that value. That means that in this case, that h is 0 at x 1 and x 2, because y is specified. Again, remember, this is because y is specified at either boundary. So, here we have at both ends we have what is called essential boundary condition or Dirichlet boundary condition. Later we can take an example where we do not specify y, then there will be a natural boundary condition, Neumann boundary condition. Okay. Let us take an example that actually gives us that natural boundary condition as well. So, as we do, let us actually consider the next problem where we minimize again with respect to an unknown function y of x, but this time we will take f to be dependent on y prime, that is the first derivative, as well as y double prime. Okay. A little extension or generalization, instead of taking only first derivative we also take the second derivative, right. This is the problem. We take this problem, again the necessary condition would be that the variation of this with respect to y and the arbitrary function. Now, the arbitrary function does not bother us, because the fundamental lemma gave us a way of getting rid of it to get the differential equation, and then boundary conditions, whether y is specified or not, tells us when to ignore h, when not to. Okay. When y is specified, h is 0, when y is not specified, h is still arbitrary, then what multiplies the boundary condition should be equal to 0, right. That is the thing that we will try to get here. So, that should be equal to 0, which by the way gives differential equation as well as boundary condition. This gives us differential equation, I am using dE for that, differential equation and the boundary conditions at the ends. Okay. That is what calculus of variation gives us, right. So, let us do this problem. So, if we say that Gaussian variation is 0, again we know what that gives, which is that we have x 1 x 2 dou f by dou y into h plus dou f by dou y prime into h prime plus dou f by dou y double prime into h double prime dx equal to, that is the first step in the Gaussian variation. This from the definition, again definition of Gaussian variation to recall for you is d by d epsilon of that j, where you replace y with y plus epsilon h and then substitute epsilon equal to 0. That is what we did for 1. Now, we have done it for the case where there is also y double prime in addition to y and y prime. That is what you get when you do this. Okay. There is no trick there, this is the definition. There is limit definition which is equivalent to this, and that is what we have done. Okay. Now, earlier we did integration by parts to get rid of this h prime. Now, we have to do that 2 times, we have to integration by parts twice to get rid of h w prime, h prime, h double prime into h. First h double prime becomes h prime and then becomes h, right. So, let us do integration by parts twice. So, integration by parts once, integration by parts, if we do, we get, we leave alone the first term as it is, we do not touch it because that already has h, which is good enough for us to apply the fundamental lemma dx. Let us put that, and let us take the second term. Let me write second terms using blue color. So, you are clear where it is going. So, that I will do integration by parts. The first function dou f by dou y prime, integral of the second function which becomes h, evaluated at the boundary x1 x2 minus integral of x1 to x2 dou f by dou y prime. We have to do derivative of the first function into integral of the second function dx. Okay. That takes care of the second term. Now, let me use green color for the third term. We do integration by parts for that. You get dou f by dou y double prime first function, integral of second function. Second function here is h double prime. Okay. Now, if you do integration once, that you get h prime. This you have to evaluate at the 2 boundary points x1 x2 minus x1 to x2 derivative of the first function, that is d by dx of dou f by dou y double prime, integral of second function, and then there is dx. That should be equal to 0. We did integration by parts once. Let us do it one more time. Okay. So, now we do integration by parts again, integration by parts again a second time we want to do. Again, let me use the color coding. The first term that we have, it remains as it is, dou f by dou y times h dx plus, let us go to the second term which is already there is nothing because there is h here, there is h there. So, I will just write that dou f by dou y prime h at x1 to x2. We do not need to do integration by parts for the second term as well, x1 x2 d by dx of dou f by dou y prime into h dx. Now, for this term, the boundary term part is fine, that is already h prime is there, that does not bother us because in the boundary condition dou f by dou y double prime h prime x1 x2. What we will do is for this term, that is for this, to get rid of this h prime, we will do integration by parts one more time. That gives us, now we take this one as the first function, that is we take this one as the first function. So, I can write minus, because the minus sign is there, d by dx of dou f by dou y double prime first function, integral second function, first function is that, integral of second function is h prime, that becomes h, that will be the boundary condition x1 x2, and then minus, there is a minus already. So, minus of minus plus derivative of the second function that we derivative of the first function already had d by dx, another derivative d square by dx square of dou f by dou y double prime, integral of the second function, that is h dx. and the whole thing should be equal to 0. Okay. Now, we can collect all the terms. There are integral terms. So, this is an integral and this is an integral, this is an integral. Let us collect all of them as one, x1 to x2, what I have dou f by dou y, this has h, this has h, this has h. So, we will take h there out. So, minus d by dx of dou f by dou y prime plus d square by dx square of dou f by dou y double prime, all of this times h. Okay, that is what we get, integral part, which we say must be 0, because integral and boundary terms both being 0 will be true only for some specific h, but h is arbitrary. So, we actually separate out the boundary terms and the integral terms. So, we got our differential equation. So, this is our short form for differential equation, right. Differential equation will come if we apply the fundamental lemma, which is that whatever we have here, that is our phi. Okay. We had used that argument that phi times h should be equal to 0 for all arbitrary h, the phi should be equal. So, our that is phi equal to 0, meaning we have dou f by dou y minus d by dx of dou f by dou y prime plus d square by dx square of dou f by dou y double prime equal to 0. We got our differential equation and the boundary terms are also there. Let us write them. So, we can see them also. Take a look what we have. There is a boundary term here which has h, there is a boundary term here also that has h, there is another boundary term here that has h prime in it. Okay. So, we will collect the ones that have h and h prime separately. Okay. So, remember this is dou f by dou y prime h, this is minus d by dx dou f by dou y double prime times h. So, the boundary conditions now if I write. So, I have dou f by dou y prime that had h, and then we also have d by dx of dou f by dou y double prime, both of these multiplied by h at either end x1 x2, right. So, now we took care of this, we took care of this, then we have this also, right, that let us write dou f by dou y double prime h prime. So, plus dou f by, was it plus or minus, that is plus, minus was only here, dou f by dou y double prime into h prime. Here it is h prime x1 x2 equal to 0. So, we separated out the differential equation integral part and the boundary conditions. Now, boundary conditions too, you can have the sum that we have written being equal to 0 in some cases, and those cases are not rare. Okay, it will be for boundary conditions, certain boundary conditions h and h prime together can give you, or you can make them separate, that is more common. The other one is also possible, but that is less common, where the sum of these two that we have written is equal to 0, but most often individually these two things being equal to 0 is common. So, we will write it that way, but remember that there could be cases where both the terms summing to 0 is also possible as a boundary condition at x1 and x2. If we separate out, which is the more common case, what we say is that dou f by dou y prime minus d by dx of dou f by dou y double prime times h equal to 0 at either end, okay, and dou f by dou y double prime into h prime at either end x1 x2 equal to 0 is possible separately or together sometimes. Together also we will consider later, but right now let us separate out. So, we get the boundary conditions. Okay. Now, when is h 0? When y is specified, if y is specified, h is 0. Similarly, if y prime is specified, h prime is 0. When it is not specified, this other part is equal to 0. When h is not specified, that is 0. When h prime is not specified, this is 0, like what we considered earlier. Okay. In order to make sense out of this, we should take an example of an integrand that has first and second derivative in it in addition to the function. So, let us take an example where I want to minimize. This is what we call potential energy, because we discussed this minimum potential energy principle, which gives you static equilibrium with respect to a function. Here let us take that function to be Wx, which has a physical meaning, which is like a beam. If I have a beam and there is some loading on it, let us say there is a loading on it Qx, and let us say this deforms, okay, in some fashion. There can be any boundary condition, let us say that deforms in a particular fashion. There is at different points we will have deflection Wx. So, x is like this, x equal to 0 here, x equal to L there, span of the beam. Everywhere we need to find this function Wx. How do we find? We find it by minimizing this potential energy. The potential energy we will write 0 to L. So, for what we are writing x1 to x2 becomes 0 to L. Potential energy, that we will discuss later how we get the expression I am going to write. For now, let us just take it. So, potential energy here can be written as half what we call Young's modulus and second moment of area I for the beam, okay, into d square W by dx square minus q of x times W dx. Okay. That is what is potential energy. We can discuss later how that comes about, or maybe you already know from beam theory that potential energy for beam can be written in this fashion. So, what we have here, this Pe, we have integral 0 to L like an integrand, okay, which depends on W, the W is there. We also have that this depends on d square W by dx square dx. There is no W prime here, but second derivative is there. If you have this, if you write the Euler Lagrange equations that we just derived, we get the equation. Okay. Let us do that quickly. So, we have dou f by dou y, that becomes W, minus d by dx of, this is d by dx of dou f by dou W prime we write, and then plus d square by dx square of dou f by dou W double prime instead of y double prime equal to 0, right. Let us go up and see that that is what we had as the equation, right. So, dou f by dou y d minus d by dou f by dou y prime d square by dx square over dou f by dou y double prime. Now, W our function, so y has become this. If we do this, what we get dou f by dou W, look at our f here, which is that W is over there, that gives you minus q, and then second one is 0 because there is no W prime there. W double prime is there, d square W by dx square is there, right. So, that is plus d square by dx square of dou f by dou W double prime, that gives us the square and 2 go away. So, I get E I into d square W by dx square equal to 0. and this must be familiar to you. So, what we have here is, what this gives us is d square by dx square of E I d square w by dx square equal to q, because it is minus q on other side, and in fact if E and I do not vary with x, like constant cross section beam, it will become E I fourth derivative of w equal to q. That is what you would have learnt in Euler Bernoulli beam theory, where you have force balance and gotten the solution. Now, we minimized potential energy, got a solution. Not only that, we also will have boundary conditions. Okay. If you write down the boundary condition, which I will leave as an exercise to you, for this one you have f here and f, and y becomes your w. If you write it, then various boundary conditions, I did not say what boundary, it can be pinned, fixed, guided and so forth, which we will consider in the next lecture, but you can try the boundary conditions here and make sense out of these Dirichlet boundary conditions and Neumann boundary conditions are essential and natural. So, we will consider that in the next lecture. Thank you.